So for the beginning, just let me introduce myself. I'm coming from Romania. I'm professor at the Lucian Blaga University of Sibiu, the Department of Mathematics and Informatics, and director of the Research Center in Informatics and Information Technology. My presentation from today is intended to be a tribute to the memory of Professor Julian Lavrinovic, who I met in 2007 in Sofia while waiting to go to the conference in Borovets in the same accommodation in the Academy of Sofia. So then I had the opportunity to see the work of Professor Lavrinovic. He sent me a lot of articles, and afterwards we had the opportunity to participate in 2009 and to one of the hypercomplex seminar in Bedlevo. Was a very nice experience, but I didn't repeat it afterwards because my interest changed and I focus more on informatics, on artificial intelligence and machine learning. And this year I was happy to see that these trends in applying machine learning in almost every field offer me the opportunity to participate to a hyper-complex seminar with a topic that I believe to fit with the seminar and to be somewhere between mathematics and informatics. Anyway, machine learning has a very strong mathematical background, so it can be of interest both from computer sciences and for mathematicians, and also for other specialists in connected fields that want to apply machine learning, because it's just like a trap to see. Everyone can say, oh, it's very simple, we can apply machine learning, but if you don't understand very good what's happening there, there is a danger that your results not be representative and maybe to be just an impression that you solve this problem. This was my short introduction. It's exactly 4 o'clock. So I think we can start with the presentation if you agree. So my presentation is entitled Methods for Parameters Optimization in Support Vector Machines and Support Vector Regressions, and focuses on a very current problem in machine learning, the problem of parameter optimization, and one of the issues of the issue of machine learning. Even if the other two presenters just enter a little in machine learning, I would like to present you very brief what is the difference between the machine learning and the classical programming, because practically machine learning appears like a new paradigm. Then to present the goal of my article together with some basic notion about support vector machine and support vector regression that are techniques in supervised learning is the other part of learning. Professor Tmucea presented the unsupervised learning, so you can have maybe a larger image of machine learning direction. Then the main part of the optimization, the kernel trick and the automatic optimization of multiple kernels without equation, without mathematical very strict part, but using many many methods taken from nature. So in the classical paradigm of programming, we have the input data and the output data, and we are just looking for the rules that represent the algorithm that maps the input data to the output data. And we write this algorithm in order to obtain the output data. In the machine learning approach, the paradigm is different. We have a set of input data together with output data, and the algorithm just try to build or to learn the model that maps the input data on the output data for unknown data. So this is practically the difference. So we need a lot of data. And this is not a very difficult problem, because now we have a lot of data, but unfortunately, these data are raw data. So machine learning cannot work very good without a pre-processing part of the data, where the raw data are transformed in structured data. And from this structured data, our learning algorithm will build the candidate model and validate afterward the candidate model using different machine learning algorithms. So machine learning can be considered divided in many directions. The unsupervised learning that Professor Kinja presented at the beginning, then supervised learning, and another type, reinforcement learning. They are all based on data, but in the case of unsupervised learning, practically the algorithm will find itself this hidden connection between data, as we could see before. In supervised learning, we have this so-named training data set, that means pair of input and output, and this training data set will guide our algorithm to learn the mapping between the input and the output. And reinforcement learning also, it's a very interesting direction that is inspired from the real learning process. Looking to human, not necessarily now, maybe not now, not exactly like this, but before, if somebody had good results, he will be awarded. But if it has low result, it will be punished. It's the same with the algorithm that we introduce in reinforcement learning. So just the punishment and the awarded will be made on some probabilities that are assigned to different operations to be made. In my talk, I will focus on supervised learning, just one technique from supervised learning. In supervised learning, as I said before, we want to learn a model to map the input data to the output data. The simplest model we can consider to be a function. And if this function is a function with discrete values, we will have a classification. So we can decide if one data lies in one class. And if this function is a real values one, we will have a regression problem. So we have a prediction. We will predict a real value for an input data. So this is practically the main problem. The easier problem is the supervised learning of function. We have an unknown function. We just have this pair xi. X represented the name input vector with a number of attributes with different types. And we want to learn a target function. This target, the target function is the real function that we don't know. And we will learn a function named hypothesis that approximate a target function, and the method that we choose will decide how we construct this hypothesis, how our algorithm will learn this function. So in supervised learning, there is an issue that can be named as induction learning. So we learn a model, and our model behaves very good on training examples, and we will suppose that our model will also behave good on other examples. But this is just a supposition, and we need to verify it. There are many methods. I just figured out here a few of them: decision trees, neural networks, support vector machines, with their equivalent for regression trees. Neural networks work both for classification and regression, and the equivalent of support vector machine is support vector regression. So in my presentation, I consider these techniques of support vector machines that include also support vector regression. And in the following, I will present you just mathematical formulation of support vector machine methods and the way in which we can optimize the parameters that appears in this method. So one of the main issue in machine learning is the fact that machine learning, like the optimization theory, is governed by a no free lunch theorem. That means that the computational results in mean for all the methods and all the data are the same. So if one method gives me very, very good results comparing with another on one set of data, this no free lunch theorem tell me that my method will pay a lot, having a low performance for other types of data. So in machine learning, we cannot find a method to be good for any types of data. So this is the main issue. That's why we need to explore. That's why we need to know what results were obtained by others in our fields of data. That's why we need to compare many methods in order to decide which is the good one, because there is not one the best for all the data. So there is a very strong dependency on the data type. Another issue is that in these methods from machine learning, there are a lot of parameters, and the choice of these parameters is essential for the results that we obtain. Another problem is that in reality, the data are not linear separable. Of course, the techniques can be applied easier for the linear separable data, but this is not the case in the real problem. So we need to have a possibility to change from linear separable data to unlinear separable data, or maybe to find methods for non-linear separable data that can be reduced to the linear separable case. So the goal is to present methods that we propose for parameter optimization in this technique of support vector machine, using metaheuristics inspired from nature, using genetic algorithm, breeder algorithm, and algorithms inspired from wasp behavior. Support vector machine is a supervised learning method. That means it needs data, it needs pairs of input and output data, this training set of data. First, it was designed for linearly separable data and only for binary case, so and for classification. But it was generalized also for multiple classification and also for regression problems. In the case of support vector machines, we construct classifier that assure a maximum margin between the classes. And the non-separable case we will see can be handled using two types of method. One of these methods is named kernel trick, and I will present to you. So the problem that we will deal with is the simple problem of binary classification. So for a set of training example xi, iy, where iy is the value of an unknown function on xi, we have two classes that are considered to be 1 and -1, and our algorithm had to construct the equation of this hyperplane. So to learn this function f(x), and the classification of an unknown instance will be realized using the sign of our function. So if the sign is positive, we will have x star assigned to the positive example class, and if not, to the negative ones. So it is known that the form of a linear classifier can be expressed as this inner product between a weight array and x, where W represent practically the normal to the hyperplane, and bias, that is practically the distance from our hyperplane to the origin. So we have two classes of data, and we have to consider a hyperplane separating this data. But there are an infinity of these kinds of hyperplane, and the idea is which of these hyperplane to be considered in our classification. And the intuition tells us that the hyperplane that assure the maximum margins between the classes of our classification will be the hyperplane able to assure the less number of errors when we make the classification. So here is practically our classification. We had two classes. Here the round point and the square point. Here it's the normal, and B is the distance to the origin, and the distance between the margins of our hyperplane. These training examples or vectors that are situated on the parallel to the hyperplane in their extremal position are named support vectors, and they are very important because only these vectors contribute to the classification. If we classify good these vectors, of course the other ones will be also be classified correctly. So we need to learn, or our algorithm need practically to learn W and B such that to maximize these margins of our classifier. And distance between the support vector, practically this tube from here, can be expressed in the term of norm of W, and it's equal 1 over the norm of the W. And this leads us to optimization problem, a quadratic optimization problem with constraints. So we want to maximize the margins, that means 2 over the norm of W, restricted or with constraints, assuring that we have the correct classification. That means the value of the real function I and the value given by our classifier needs to be greater and equal 1. Of course, from this problem, we arrive to the other one. That means we want to minimize the square of W with the same constraints. Practically, we can solve mathematically this problem, and we have a lot of solvers. We can do this with a lot of solver. It's not a big deal. Everyone knows that this quadratic optimization problem can be expressed in its dual form using the Lagrange coefficients. We obtain the values corresponding to vector W in terms of these Lagrange coefficients, and we have the new constraints here. Solving this quadratic optimization problem, we will obtain that all the Lagrange coefficients associated to the points that are not support vector are equal 0. And this proves us that indeed only this support vector will contribute to our classification, practically, to finding our hyperplane. So what we have here is the separating hyperplane that is expressed using the Lagrange coefficient, the value of I, and very important, the inner product between the value of x and, of course, the value of the argument on which we want to find the value of f. And only the support vector are included in this sum. So this is for the case of a linear classification. What if we do not have data that are linearly separable? So we have here some points that enter inside our separating tube. So we have two possibilities. In the case when the non-linearity is not very strong, we can use a slack variable, allowing some points to enter a little in the other class. So we reformulate our optimization problem using these slack variables. And we have here 1 minus a slack variable minus 1 plus slack variables in the case of our constraints. But what is very important, the function what we want to minimize has another terms. And this term is a sum of our slack variable multiplied with a constant c, and this constant or this parameter is very important in our problem because it's practically make the trade-off between the error and the margin. So how big is our margin? How much do we let our error to enter inside? So this will be one of the most important parameters for our support vector machine method. So we have to minimize this function subject to these constraints. So this is the dual form. The dual form, of course, we obtain here the new condition for alpha between 0 and c, and of course, again, only support vector contributes to the expression of W and expression of our separating hyperplane. This is in the case where the data are not very strong non-linearly separable, but if the data are strongly non-linearly separable, we cannot apply the method before. So we just look for a map of our space of instances in another space with higher dimension in which our initial data to be linearly separable. So initially we have a space of dimension 1 and map it in a space of dimension 2. Or we have a space of dimension 2 and just map it in a space of dimension 3. And in this space, our data are linearly separable. So how can we find and how can we define these functions? So it's very hard to define. That's why we avoid to do this. So we will apply this so-named kernel trick, taking into account that in our expression of the hyperplane, we have only inner product. So our hyperplane is defined as a sum of I Lagrange coefficient and inner product between our mapping that we don't know. So we cannot just build this mapping, but in some condition, there is a bidimensional function, a kernel satisfying Mercer theorem such that the values to be equal with this inner product. And in this case, our hyperplane is just expressed using this kernel. So which kernel do we use? We don't know. We just try the same like in the other problems of machine learning. There are a lot of known kernels, the polynomial kernel, the polynomial kernel, the radial basis function kernel, the sigmoid kernel that we can use. But the problem is that in many cases, these simple kernels are not enough to allow us to model our problem. So to find a hyperplane such that to make the correct classification. And we need to find some multiple kernels combining these kernels. And it is proved that we can use the multiplication, addition, and exponential operation between kernels to obtain other kernels. So there are a lot of works regarding how to find a good kernel for our support vector machine. There are papers presenting multiple kernels, like a linear combination of simple kernels and trying to optimize the weight using a optimization theory or using evolutionary method. And what we propose here is a hybrid approach that allows to optimize the multiple kernel, taking into account the specific of the data. And in this method, we use a genetic algorithm and another support vector machine to compute the fitness function for our genetic algorithm. Our method practically focuses on optimizing the parameters. That means the C parameter, the type of the simple kernels that we use in the multiple kernel, and the simple kernels parameter, because if we look here, each of these simple parameter has at least one parameter. There are implemented a lot of libraries using machine learning that realize an optimization of these parameters using grid search or using cross-validation using the data. What we propose is to use genetic algorithm and swarm intelligence-based algorithm to make this optimization. We started practically our research earlier in 2010 with some simple problems, and then developed in 2012 and 2008, and generalized the method in 2020 for regression, and just validate the method for financial data prediction. What is the idea? We have two labels in our method. In one label, we have a genetic algorithm, and this genetic algorithm will optimize the multi-kernel and the support vector machine that will compute the fitness function for our algorithm. So practically, the genetic algorithm consider a population of individuals that are practically a population of solutions, and just find an closer solution to the optimum one, using the same principle like in the evolution. Our multiple kernels is represented using a tree structure. So the terminal nodes are the simple kernels and the intermediate node are the operation. And chromosome coding the solution. So what is our solution? Our solution is a multiple kernel having three operations, because in our work we did not use more than 3 labels in our tree. Could be used more, but the computational effort is too big. So we have 3 operations. We have here the parameters in the case when all the operations are polynomial. This was our first study. Or a more complicated form of our chromosome, that means way of coding our solution, our operation, the type of the operation, and depending on the type, we have a real parameter or we have two parameters if it is polynomial. So our chromosome has 78 genes. A gene is practically a byte in our representation, and the operation has the smallest number of genes, 2 genes for coding our operation. So our genetic algorithms start for a randomly generated population of individuals that coding some solution, admissible solution. Then we evaluate this population of solution using the support vector machine algorithm and computing the accuracy. So each solution is practically a kind of support vector machine and make a classification. And we just use this fitness function to evaluate the quality of this classification. And then we modify this population using crossover operators and mutation operator. Stop criteria can be the time or can be given accuracy. We made many experiments using different commutation operators. Practically, this mutation means that in a solution with a given probability, we modify a position with another position, and in this way we make the so-named exploration in the space of the solution. The crossover, that means the combining of solution, make the exploitation of our solution. So we propose different type of operator, commutation operator, such that to obtain better performance, and also a model inspired by the WASP behavior. So practically in the WASP use a stimulus response mechanism to communicate each to other, and there is a threshold of their communication response that can be used also in our model, computational model. And we use this model to increase the probability of changing the operation, because here the operation is coded only with 2 genes, and the probability to change the operation in this chromosome is smaller than the probability to change other elements. And use this WASP behavior, computing practically the accuracy such that to obtain better results. In our WASP model, we compute a probability, the probability that a mutation operator will make a change on operation type. And then using this probability, we can modify it such that to increase the chance of the operation to change. The support vector machine algorithm compute the accuracy, and at the end, we obtain a multiple kernel that we say that is the most performant in our case. What we do afterwards, we use a k-fold cross-validation in order to validate our kernel. So we take other data that we did not use before and just verify if indeed the classification error is good enough. We implemented these using libsvm, use Java and libsvm and modify their some classes and some methods in order to perform our method, and use some toy data set in the case of classification, leukemia, and data set and vowel data set. And here you can see our results. What is with star means that we use this WASP algorithm, and the other we did not use it. Also, the number of the method, number one means we use a classical mutation, and to the other, we change our mutation. So if we compare here, we see that the most complicated mutation give here a better accuracy, but it's not a very big improvement in the using the WASP method. But for the vowel data set, we can see that the accuracy is higher, and indeed it is increasing with the complexity of the mutation operation. And this proves that indeed the method is strong dependent of the type of the data. I think I have more time, or I'm over. And in support vector regression, that means when we want to predict a real value, the function that we optimize is different. We use an insensitive loss function here, and we have the same mathematical formulation, the same frame like in the case of the support vector machine. Just we'll have one more parameter here, the parameter epsilon that appear here in the constraints, because here we have a real prediction. We do not have 1 and -1 like in classification. And of course, we have the multi-kernel that we want to construct. The difference is that we use a breeder genetic algorithm instead of a genetic one. The breeder genetic algorithm coded the solution using real values. So here we will have only real values, a number of 21 real numbers that characterize a solution. That means a kernel, a multiple kernel that we want to obtain, together with the parameters C and P is this epsilon in our constraints. And using this breeder genetic algorithm, we evaluate the population and evaluate it until we find, taking into account our stopping condition, close to optimum solution. Here I just presented the crossover in the case of the breeder genetic algorithm, so how we combine two solution xi in order to introduce in the new generation another solution. Then the mutation is different in the case of the breeder genetic algorithm. Also here it's the rule. The rest is the same, just we choose only elements from the T% best elements of P. And another difference is that the fitness function is the MSE function computed here. We also implemented it in Java using lib7m modify function and classes, and evaluate our method on financial series from different indices and monthly and weekly series, and evaluate using different metrics and comparing with different other methods. Here it's our method. This is a simple support vector regression with only RBF kernel, an ARMA-JET method, and our method gives better results for these financial data set. So practically, we can improve automatically the parameters and to find a good kernel depending on the data. But the method has to be applied to different type of data in order to find a good kernel. Yeah, this was briefly the content on my presentation. Thank you.
Yes, thank you very much. Do we have any questions?
I would like only say that it was excellent presentation.
Thank you.
Now, what about the processing time? If you test,
in general,
algorithm is quite computationally demanding, as I
but the problem is that with the possibility that we had when we ran this, it took some days in order to obtain the results. But this is the problem generally in machine learning, and especially in support vector machine, more even that to the neural network. We need a long time to train our model. But afterwards, if we have trained the model and the results are good, we can just in time apply the model to other unknown data.
Yeah, so you mean the inference time is quite fast?
Yeah.
Okay.
Yeah, it's just in time. Say just apply, introduce into the model the value and obtain the results. And there is also the possibility to improve the model. So we have a model, we save the model, and we can improve it afterwards with new data. So if we have new data, we can start not from zero, but from an existing model, and just to develop it more such that to fit with the other ones.
Okay, thank you very much. So we don't have more questions.